Hello guys, in this video I'm going to be teaching you stoichiometry and limiting reagents. Here we are going to be considering introduction to stoichiometry. Then we look at limiting and excess reagents. Also, we will look at methods of identifying limiting reagents in chemical reactions. Then consider some calculations related to stoichiometry and limiting reagents. So let's get started. What is stoichiometry? Stoichiometry is a branch of chemistry that is concerned with the relationship between the reactant and the product. For example, we have A is equals to B. This is a stoichiometry reaction because it is concerned about the reactant A and product B. Another example is A plus B, giving us product C. This is a stoichiometry reaction because it is concerned about the two reactants A plus B and relationship with product C. What are the parameters that we can be given in stoichiometry reactions? The parameters are weight, which is also known as mass. Then we have mole. We have volume if gas is involved. Then we have concentration. Now in stoichiometry reaction we have two areas. Let's consider the first case. Case 1. Considering a simple chemical reaction. For example, we have A plus B is giving us product C. In simple chemical reaction, for example, I'm giving the weight of reactant A to be 3.2 grams. And we are asked to solve for the weight of the product C or the weight of the other reactant B. But in a simple chemical reaction, we are going to be giving the weight of one of the reactants or the product. We can also be giving the mass of B, let's say 5.8 grams, and we are not giving the mass of A. So in a simple chemical reaction, we will not be giving the masses of the two reactants, but one of the reactants will be given. Then with the one of the reactant given, we can calculate the others. That means we can calculate, if I'm giving the mass of B, which is 5.8 grams, I can use that to calculate the mass of A or the mass of C. We can also be given the mass of C, let's say 7.2 grams. Then we are asked to solve for the mass of the first reactant A or reactant B. But in a simple chemical reaction, we are not going to be giving the masses of the two reactants. Another example, let's say we have C plus D is equal to E as product. We can also be given the concentration of D, and we are asked to solve for example, is 0.2 molar. We have considered concentration in the previous videos, so you can feel free to check it out so as to make you understand what we are doing in this video. So we can be given the concentration of D, and we are asked to solve for the concentration of either C or we are asked to solve for concentration of E. So in simple chemical reaction, we'll be given one of the reactants or the product, the parameters related to one of the reactants or the product. Now let's consider case 2. Case 2 is talking about a complex chemical reaction. In a complex chemical reaction, where we are given parameters related to the two reactants. For example, we have A plus B is giving us C, and in this case we are giving the mass of A to be 2.1 grams and also giving the mass of B to be, let's say, 0.8 grams, and we have to solve for the weight of the product C. Here we cannot use a simple comparison method to solve this because we don't know the one we are going to compare. Maybe we are to compare reactant A with the product C, or we are to compare reactant B with the product C. So in a complex chemical reaction, we are going to be given parameters related to the two reactants involved. Then we are asked to solve for the product. Here, the first thing is to be able to know the one that is the limiting reagent, and we are going to discuss this later in this video. Another example is if we have reactant P plus Q and we are having product R plus S. In a simple chemical reaction, we'll only be giving the parameter for either P or Q. But in a complex chemical reaction, we are going to be giving parameters related to the two reactants. For example, we are having 1.5 gram in terms of weight, and we are giving 0.3 gram of the second reactant Q. So in this case, we cannot just pick reactant P and use it to compare one of the products, either R or S. And we cannot just use Q to compare with R or S. Before we can do a complex chemical reaction calculation, the first thing is to know the one that is the limiting reactant. That is all about stoichiometry. So in stoichiometry, we are interested in the reactant and the product, whereby we are giving some parameters related to the reactants and we want to use to solve for the product, or we are giving parameters related to the product and want to use to solve for reactant. So let's look at some examples related to simple chemical reactions, whereby we are giving parameters for one of the reactants or the product, and we have to solve for parameters related to one of the reactants or products. As you can see on the screen, we have 0.5 gram of magnesium solid react with hydrochloric acid. According to the reaction, Mg plus 2HCl will give us MgCl2 plus H2 gas. The first question says we should calculate the mass of magnesium chloride that is produced. Second says determine the volume of hydrogen gas given off. So how are we going to do this? Like I said, this is a simple chemical reaction because we are only giving the mass of one of the reactants. We have two reactants here, which is magnesium and hydrochloric acid. We are giving the mass of magnesium, which makes it a simple chemical reaction, assuming we are giving the mass of magnesium as well as hydrochloric acid, so that being a complex chemical reaction. And in that case, we are going to be making use of limiting reagent concept to know the reactant that is being used up first. But since it's a simple chemical reaction, we just continue. The first thing is to find the molecular mass of magnesium, and we are given the molecular mass of magnesium to be 24. If we don't really know how to solve questions on mole concept, we advise we check the previous video on mole concept and Avogadro's number, so we can follow up and get things done in time. The mass of magnesium is 0.5 gram. Atomic mass, since the atomic mass of magnesium is given as 24. So with this, we can calculate the number of mole of magnesium. Number of mole of magnesium is going to be mass over molar mass, and the mass is 0.5 over molar mass, which is 24. So we are going to be having 0.021 mole of magnesium. Now we have gotten the mole of magnesium. The next thing is to compare desired product. Since the question did not say we should solve for the mass of HCl, we are not going to compare magnesium with HCl, but we rather compare magnesium with the product that we have to solve for, which is magnesium chloride. So we say that from the balanced chemical reaction, as we know, now 1 mole of magnesium is giving us 1 mole of magnesium chloride. As you can see on the screen, we have 1 mole of magnesium after we have balanced reaction with 1 mole of magnesium chloride. 0.021 mole of magnesium will also be equivalent to 0.021 mole of magnesium chloride. So we can as well say that the mole of magnesium chloride is given as 0.021 mole. Now we have known the mole of magnesium chloride. The next thing is for us to get the mass. Since the question says you solve for mass, here you are to get the molecular or the molar mass of magnesium chloride. The molar mass of MgCl2, which is magnesium chloride, is going to be, magnesium is given, the atomic mass is 24 plus chlorine atomic mass is 35.5, but we have 2 of chlorine, that is multiplied by 2, and you should be able to calculate it to be 95 gram per mole. Now we have gotten the molar mass of magnesium chloride, we can just make use of number of mole equals to mass over molar mass. Therefore, the mole of magnesium chloride is 0.021 is equals to the mass is what we are asked to solve for over the molar mass is 95. So from here, if we try to cross multiply the mass of MgCl2, which is magnesium chloride, is going to be equals to 0.021 times 95, 1.995 gram. So you see that 0.5 gram of magnesium produced 1.995 gram of magnesium chloride. That is the A part of the question. The B says that we should determine the volume of hydrogen gas liberated. Now, to note that since we have calculated the number of mole of magnesium which we are given, we can just compare from the balanced chemical reaction magnesium with respect to hydrogen gas that is liberated. I can also compare magnesium chloride. Since I've already known the mole of magnesium chloride, I can also compare that of hydrogen gas, but preferably let's use the one we are given in the question, which is magnesium. Then we say from the balanced chemical reaction, 1 mole of magnesium produced 1 mole of hydrogen gas. We check the reaction. The calculated value we have is 0.021 mole of magnesium, which simply means that the mole of hydrogen gas is also 0.021 mole of hydrogen gas. So the mole of hydrogen gas is 0.021. Now we have known the mole of hydrogen gas, then we have to solve for the volume. If we are still having difficulty in understanding how to solve more questions, I would advise we check the previous videos that I did on mole concept and Avogadro's number. And we also look at conjugation of solution in unit. There I have simplified everything we need to know about all these calculations. Here we are just solving the questions related to stoichiometry. We have discussed that the number of mole in terms of volume is going to be the volume of the gas over molar volume. Therefore, we can simply say that the number of mole of hydrogen gas we have calculated is 0.021 is equals to volume of hydrogen gas over the molar volume. Depends on the unit we want to leave it to be. We can use 22.4. We say 22.4, which is in dm³ per mole, or we can as well write it as 22,400 cm³ per mole, depending on our choice, or if the question is giving us condition, maybe to leave our answer in terms of dm³, liter, cm³, meter³. But since the question did not specify, we are simply going to make use of dm³. Therefore, if we try to cross multiply, that will give us 0.021 times 22.4, that gives us 0.47 dm³. H2 gas. So this is how we solve simple chemical reaction questions. Here we are given the mass of one of the reactants or the products that we are using that to solve for the other reactants or products. Now let's move to complex chemical reaction. In order for us to be able to solve complex chemical reactions, like we have said, that in a complex chemical reaction, it is involving two reactants giving us products, either a single product or double product, or it can even be three products. That's triple products. Here we are going to be giving the parameters. We are going to be giving parameters for the two reactants, and we can use that to solve for any of the products. But if we are given only parameters related to either the reactant A or the reactant B, then it will be easier for us to deal with. But since we are going to be giving the parameters related to the two reactants, that means we should look for a way to be able to analyze this, and that will drive us to what we mean by limiting reactant or limiting reagents. So let's consider limiting reactants. So what do we mean by limiting an excess reagent? Let's say to produce a car in the industry, we need 4 wheels and 2 headlights. If we now have 20 wheels and 8 headlights available in the industry, that's 20 wheels are available and 8 headlights are also available. With this available equipment, how many cars can we produce? Let's do the basic math. 4 wheels, 2 headlights will produce the first car. 4 wheels, 2 headlights will produce the next car. 4 wheels, 2 headlights will produce the third car. 4 wheels, 2 headlights will produce the fourth car. Then we'll be left with 4 wheels. With this, we have used up the headlights. Calculate it, we have 2, 2, 2, 2, which makes it 8 headlights. And if we calculate the number of wheels, that's 4, 4, 4, 4, 4. That gives us 20. Whereas we are still having 4 wheels in the industry, yet we have used up the headlights. From this, the excess reagents is the wheels. The wheels is the excess reagents. It is in excess by 4. While the headlight is the limiting reagents. The limiting reagents is the one that is first used up, while the excess reagent is still available. The limiting reagent, as the name implies, is the one that prevents the reaction from proceeding since it is already used up. So we cannot produce another car since we don't have 2 headlights available. That means the limiting reagent, as it is defined as the substance or reagent that is first used up in any chemical reaction. It prevents chemical reaction from proceeding. So let's say, for example, we are giving reaction between calcium oxide solid plus carbon 4 oxide gas to produce calcium carbonate solid. And we are giving the weight of the two reactants to be 5.2 gram and 8.4 gram. And we should use these parameters to solve for that of calcium carbonate. We cannot just use the weight of calcium oxide to compare with that of calcium carbonate. At the same time, we cannot just pick carbon 4 oxide to compare with that of CaCO3. The first thing is to determine the reactant that is in excess and the one that is limited. The reactant that is limited will be used to calculate the weight or any parameter related to what the question is asking us to solve for. Once we have determined the reactant that is limited, we are going to use it to solve for the weight of the product in this case. Since we have understood what we mean by limiting and excess reagent, the next thing is to learn how to identify the limiting and the excess reagents in any chemical reaction. So there are two approaches that we can use to identify the reactants that is limited. So let's start with the first approach. So the first method of identifying the limiting reagent, we have 4 steps. The first thing is that we determine the number of moles of each reactant. That is, if the reactants are not expressed in moles, if they are expressed in mass, then we have to convert to moles by using mass over molar mass. But if the reactants are already expressed in moles, then we'll just move to step B, which says that divide the number of moles of each reactant by its stoichiometry coefficient in the balanced chemical reaction. For example, if I'm having 2A plus 3B is giving us C. After we have determined the number of mole of A to be, let's say, 0.5 mole, then we'll divide it by saying 0.5 divided by its own stoichiometric coefficient is 2. That is divided by 2, we get its value. Then B, let's say the mole of B is 1.5. Then we say 1.5, which is its mole, over its own coefficient, its stoichiometric coefficient is 3. Then that will be 0.5 divided by 2, then 1.5 divided by 3. Then the step C says that after we have divided by their stoichiometric coefficient, the reactant that gives us the smallest value is the limiting reactant. That means if I divide 0.5 by 2, that will give us 0.25. Then 1.5 divided by 3, that will give us 0.5. 1.5 divided by 3 gives us 0.5. So between 0.5 and 0.25, 0.25 is lower or less than 0.5. That means A is the limiting reagent. Now let's look at this example 2. It says that what will be the limiting reagent if 75 grams of C2H3Br3 reacted with 50 grams of O2 in the following reaction. The reaction is already balanced. We just want to determine the limiting reagent. Since we are given the mass of the first reactant, which is C2H3Br3, we are given the mass of the second reactant, which is O2. The next thing is that we need to convert their masses to mole by saying number of mole equals to mass over molar mass. So its own number of mole, let's label it as 1. Let's say this one is 1, the first reactant, and this one is 2. So that means N1 becomes mass over molar mass or molecular mass. So in that case, the mass of the first reactant is 75 divided by its own molar mass is already calculated and is given as 267. So be able to get its own number of mole. Then for the second reactant, which is N2, is going to be mass over molar mass as well. Its own mass is 50 grams. Then its molecular mass is 32. So we are going to have 0.281 mole of the first reactant. The second reactant is 1.563 mole. That's the first step to determine the number of mole of the reactants involved. The second step is to divide this mole we have calculated by their stoichiometry coefficient. We check the first reactant, its own stoichiometry coefficient is 4. The number of mole here is 4. Then for the second reactant, its own is 11. So let's get the value. Its own number of mole is 0.281 divided by 4. Get the value. Then for the second one is 1.563 divided by its own coefficient is 11. And in that case, we are going to have 0.07, 0.142. So after we have followed the step B, which says that divide the moles we have calculated by the stoichiometry coefficient. For the first reactant, its own stoichiometry coefficient is 4, and when we calculated it, it's giving us 0.07. While for the second reactant, its own mole is 1.5 divided by its own stoichiometric coefficient, which is 11, and that is giving us 0.142. So if you look at the two, 0.07 is less than 0.142. Since it is less than, that means the first reactant is our limiting reagent, and it is the one that will determine the end of the reaction. And this is how we identify the limiting reagent in a chemical reaction, by using the first approach. Here, C2H3Br3 is our limiting reagent, while oxygen is the excess reagent or reactants. Now let's look at the second approach on how we can identify the limiting and the excess reagents. In the second approach, it's similar to the first approach that says determine the number of moles of each reactant, provided that the reactants are not expressed in moles. If they are expressed in moles, they will move to step B. In step B, it says that use each reactant to find the mass or mole of the main product. For example, let's say we have 2A plus B is giving us C, and we know the number of mole of A and the number of mole of B. Here we are going to compare the A with respect to C. We also compare B with respect to what? C. So the one that gives us, the one that provides the lowest value of the product is the limiting reagent. That is the second method. So second method, the step B says use each reactant to find the mass or mole of the product. Then the one that yields smallest value of the product is the limiting reagent. Now let's take a look at example 3 to help us understand how second method works. Calculate the number of mole of C formed in the reaction. 2A plus 4B is giving us 3C plus 4D. When 5 moles of A react with 6 moles of B. Let's try to use the second method. We are having 2A plus 4B is giving 3C plus 4D. Here we are going to use the first reactant with respect to the product. Since the cell should be for C, so C is our main product here. So we compare the first reactant, which is A, with respect to C. Then we have a particular answer. Then we also compare B with respect to C. We still have another answer. So we compare the two answers afterwards to know the one that is having the smallest value. So let's look at it together. Here, according to the balanced chemical reaction, 2 moles of A is giving us 3 moles of C according to the reaction. But in the question, we are giving 5 moles of reactant A. Since we are giving 5 moles of reactant A, we now say, therefore, 5 moles of A will produce X, which we can simply cross multiply. Then we'll be having 5 times 3 is equals to 2 times X, which is 2X. Then we are interested in X. So X will simply give us 15 over 2, which is 7.5 mole of C. Now we have gotten the value of C when we compare with A. Now let's check the second reactant. Now we want to compare B with C, that second reactant. So we say, according to its own balanced chemical reaction as well, 4 moles of B produced 3 moles of C. Therefore, B, its own mole in the question, is 6. Therefore, 6 mole of B will produce Y. Don't want to use X again. Though these are basic chemistry, we can as well jump all these basic steps and solve it at once. So when we try to cross multiply, be having 6 times 3 is equals to 4 times Y, which is 4Y. So that will give us Y is equals to 18 over 4. Then that is going to 4.5 mole of C. So here we have 2 values of C. The first reactant, which is A, when we compare with the product C, we are obtaining 7.5. But the second one is giving us 4.5. Here, then we look at the 2. Since the second reactant is giving us the lower value, which is 4.5, then we can say that reactant B is the limit reagent, since 4.5 is less than 7.5, and 4.5 is obtained from B when we compare with respect to C, while 7.5 is obtained from A when we compare with respect to C. So in this case, the limiting reagent is reactant B. So this is the second approach you can use to solve limiting reagent and to identify it. We can also use the first approach to solve this same question. Since we are given the moles of the 2 reactants directly, we don't need to convert to mole. We just divide the moles by the stoichiometry coefficient of the reactants. Here, the mole of A is 5, divided by its own stoichiometry coefficient is 2, divided by 2, and that gives us 2.5. That's for A. Then for B, its own mole is 6, divided by stoichiometric coefficient here is 4. So we are going to be having 1.5 for B. Then we can say, according to what we have done, that means 1.5 is less than 2.5. Therefore, the B is our limiting reagent or reactant, while A is known as excess reagent. So since B is the limit reagent, it is the one that will determine the end of the reaction. Since it's already used up, that means the reaction cannot proceed. These are the 2 ways of identifying the limiting and the excess reagents in a complex reactions. Now let's go to some examples to help us understand how to solve questions anytime we come across limiting reagents calculations. So let's consider this example so as to make us understand how to solve questions related to stoichiometry and limiting reagents. Consider the reaction NH3 plus O2 gives us NO plus H2O. In an experiment, 3.25 grams of NH3 are allowed to react with 3.50 grams of O2. Which reactant is the limit reagent? How many grams of NO are formed? How much of the excess reactant remains after the reaction? The first step is to balance the reaction. As you can see on the screen that the reaction is not balanced. So you can either balance it by writing it as 2NH3 plus 5 over 2O2 to produce 2NO plus 3H2O. If you want to balance it this way, you can as well write it as 4NH3 plus 5O2 produce 4NO plus 6H2O. Either ways we are correct and we can confirm that. Now the next thing is to calculate the number of moles of the reactants. As we have said, we need to convert the masses of the reactant to moles according to the first approach that we have discussed previously. Now, let's take the first reactant to be 1 and the second reactant to be 2. That means we say N1, which is the number of mole of the first reactant, is going to be mass over molar mass. The mass of the first reactant, which is ammonia, is, you can see, is giving us 3.25 grams of NH3. That will give us 3.25 over molar mass of NH3. As we all know, NH3, that nitrogen is 14, while hydrogen is 1. So we can say that NH3 molecular mass is going to be 14 plus 1 times 3, and that gives us 17. So as over 17, that will give us 0.191 mole. Then the number of mole of the second reactant, which is oxygen, is going to be mass over molar mass. The mass of oxygen given is 3.5. The molar mass of oxygen gas is 32, and we are going to be having 0.109 of oxygen. Now that I have calculated the number of mole of the two reactants, the next thing is to divide the number of moles by their stoichiometric coefficients. For the first reactant, which is nitrogen, its own stoichiometric coefficient is 4, as you can see, is 4. So that means we are going to say 0.191 over 4, we obtain 0.0478. Then for oxygen, the number of mole of oxygen is 0.109. You also need to divide it by the stoichiometric coefficient. Stoichiometric coefficient of oxygen is 5. So we have it to be 0.0218. Now, if you look at the two values, that is 0.0478 and 0.0218. 0.0478 is greater than 0.0218. That means since 0.0218 is less than 0.0478 and 0.0218 is produced by oxygen, that means oxygen is the limiting reactant or reagent because its own value is less than the other one, which is NH3. So we have solved the first question. So the limiting reactant is oxygen gas, and it's going to determine the end of the reaction. The B part, how many grams of NO are formed? Like you have said, the limiting reagents are first used up and they are used to calculate the parameters related to the product. Since oxygen is the limiting reagent, that means we are going to be using oxygen to calculate the parameters related to the B part by considering the balanced chemical reaction that says 5 mole of oxygen produced 4 moles of NO according to the balanced chemical reaction. Therefore, the number of mole of oxygen in the question is 0.109. We are not going to make use of 0.0218. 0.0218 is just used to get the limiting reagent. The mole of oxygen itself is 0.109. Do not mistaking 0.021 for the mole of oxygen. 0.109 mole of oxygen will be equivalent to 0.109 times 4 over 5. That is for NO. So the number of mole of NO is giving us 0.0872. But the question did not say we should solve for number of mole but mass. That means you need to get the molar mass of NO so as to get the mass. Molar mass of NO, nitrogen is 14, oxygen is 16, and that gives us 30 gram per mole. So according to the formula, number of mole equals to mass over molar mass. So we can simply write it as number of mole calculated for NO is given as 0.0872 is equals to mass over the molar mass of NO is 30. We must multiply mass of NO in terms of gram is going to be 2.62 gram. Now we have calculated the B part by using the limiting reagents. Then the C part says that we should know the amount of the excess reagent that is left. In order to do that, we need to know the number of mole of the excess reagent that reacted with the limiting reagents. How are we going to do that? Since we have said that the limiting reagent is the one that is used in calculating the parameters related to other things we have to solve for. So the next thing is that we need to compare the limiting reagent with the one that is excess. So the limiting reagent, according to the balanced stoichiometry reaction, you can see it that 5 moles of oxygen reacted with 4 moles of NH3, which is ammonia. So we say 5 moles of O2 reacted with 4 moles of NH3. Therefore, 0.109 mole of oxygen will react with 0.109 times 4. We are cross multiplying over 5 of NH3, and that will give us 0.0872 mole of NH3. This simply means that the number of mole of NH3 that reacted with 0.109 mole of oxygen gas, which is limited, is 0.0872. 0.0872 mole of NH3 reacted with 0.109 mole of oxygen. Therefore, we can calculate the mass of NH3 that reacted by saying mass is equals to number of mole times molar mass. The number of mole is 0.0872 times the molar mass of NH3 is 17, and from there we can have our answer 1.48 gram of NH3 that reacted. That means out of the 3.25 gram of NH3 that was given, it was only 1.48 gram that reacted. That means the amount of NH3 that will be left, that is the one that did not react, is going to be mass of NH3 that wasn't used up, is going to be, the one given is 3.25 minus 1.48. And we have it to be 1.77 gram. So out of 3.25 gram of NH3 that was given, it was only 1.48 gram that reacted. Let's consider this example. Consider the reaction C6H6 plus Br2 produce C6H5Br plus HBr. That is to say, benzene reacting with bromine, that is halogenation of benzene to give us bromobenzene and hydrogen bromide. What is the theoretical yield of C6H5Br, that is bromobenzene, if 42.1 gram of benzene reacts with 73.0 gram of Br2? If the actual yield of C6H5Br is 63.6, what is the percentage yield? Can feel free to pause the video so as to try it. Okay, so let's continue. The first thing is, let us determine the molecular mass of the two reactants. As you can see, it's a complex reaction. It's not a simple chemical reaction because we are given the masses of the two reactants involved. So the first thing is to know the one that is limiting reagent and the excess reagent. So before we do that, let's first know the molecular mass of the two reactants. Molar mass of Br2, bromine is 80 on approximation, and we have 2 of it, so that will give us 160 gram per mole. Then for molar mass of the first reactant, which is this is H6, that gives us carbon is 12 times 6 of carbon plus hydrogen is 1 times 6, and that should be giving us 78 gram per mole. Now that we have determined the molar masses, let's know their number of moles. Let's take the first reactant to be 1 and the second reactant to be 2. That means the number of mole of the first reactant is going to be mass over molar mass. The mass of the first reactant is 42.1 as given in the question, divided by its molar mass is 78 gram per mole. Then for the second reactant, which is bromine molecule N2, the mass given is 73 gram of bromine molecule, 73 over its own molecular mass is 160. So we're able to get the number of moles of the two. So for first one, we have 0.539 mole. Then for bromine molecule, we have 0.456 mole. The next step is for us to divide the mole by their stoichiometry coefficient. If we check the balanced chemical reaction, since the reaction is balanced, 1 mole of benzene is reacting with 1 mole of bromine molecule. So we divide it by the stoichiometric coefficient, and that will give us change the ink. That gives us 0.539 divided by 1. Its own stoichiometric coefficient is 1. That gives us 0.539. No unit since it is mole ratio. Then for the second reactant is 0.456 divided by 1, and that gives us 0.456. So if we consider the two, 0.456 is less than 0.539. That's to tell us that bromine is limited. Bromine is having a lower value than benzene. So bromine molecule is the limiting reagent. Now that we have determined the limit reagent, it is useful because the limit reagent is used in determining the parameters needed for the products. So since we have known the limit reagent, then we can use it to calculate the product. And in the question, we are asked to solve for the theoretical yield of the main product, which is bromobenzene, and the other product is hydrogen bromide. So in that case, if you consider the reaction of the limit reagent, which is bromine molecule, and the product, which is bromobenzene, you notice that they are having 1:1 ratio in their mole. So we can compare by saying 1 mole of bromine molecule produced 1 mole of bromobenzene, C6H5Br. Therefore, the mole of bromine molecule is 0.456, and that means we are going to be having 0.456 times 1/1 to get that of bromobenzene, and that's the number of mole of bromobenzene is given as 0.456 4, 5, 6. So we can calculate the mass of bromobenzene since we have gotten the mole. The molar mass of bromobenzene, which is C6H5Br, is going to be carbon is 12 times 6 plus hydrogen is 1 times 5 plus bromine is 80. We're having 157 gram per mole. Now we have gotten the molar mass of C6H5Br. We can calculate its mass by saying number of mole equals to mass over molar mass. The number of mole of bromobenzene, as we have calculated it to be 0.456, is equals to mass over the molar mass is 157. So the mass becomes 157 times 0.456, and the mass gives us 71.6 grams of the main product. Since we have gotten the mass, that's the theoretical yield of the main products, the B part says we should calculate the percentage yield. The percentage yield formula is given as actual yield over theoretical yield times 100, and we can have our answer to be the actual yield given in the question is 63.6 over 71.6, which is the theoretical yield. That's the calculated yield times 100, and that we are going to obtain 88.83%. Since we have looked at examples under stoichiometry and limiting reagents, these are exercises that we should try when we are less busy, and you can send your answers for me to help you cross-check it through the comment section. Thank you.